hammer on this, but what you've got in here is a big old power supply. This is a 24-volt power supply. This is the AC input that comes in the bottom. You can see my cursor. Somebody, does my cursor come across?
Smoke out.
Roger, team, does my cursor come across on your desktop?
Yeah. Yeah,
Okay.
It's a little jumpy, but we can see it.
All right. So 24-volt power supply. The EtherCAT systems use a 24-volt power supply, and there are two parts in the architecture. One part is the part that runs the EtherCAT bus and associated logic, the actual signaling. The other 24-volt runs all of the I/O on the slices. Okay. Then there might be a third power supply that supplies power to high amperage devices like motor drives. And sometimes you'll see a 48-volt supply that is dedicated to running one of those kinds of devices. So on this system, you'll see the 24 coming in, right? Or excuse me, the 120-volt coming in down at the bottom. With me? Somebody say yeah. Okay. Then up here, we've got the 24-volt coming out. And if you look in the architecture right here next to the IPC, right? What is this? Integrated Personal Computer, I think is what that stands for. That's a CX2030. This is actually a Windows CPU. It's running a Windows OS on this. Has a hard drive. If you were to plug into this port, you would actually see a video output like a regular desktop. Okay, this is the IPC itself. The power for it comes in on this slice over on the left. There's a 24-volt input that runs the PC and all of the I/O slices bus, and then there's a second 24-volt link that runs the actual input-output and drives all of the field wiring on the slices. So it's not one hookup, it's two. Sometimes it's one power supply, sometimes it's two power supply, depending on whether or not they want to disable I/O and leave the PC running. Sometimes you'll see things like uninterruptible power supplies in these things to keep the CPU hot so that it can store its state before it shuts down. There's a bunch of things that can happen in there, but this is the PC. As I mentioned, it does have a Windows desktop, so you can plug in a USB keyboard, USB mouse, and this is a video output, but you have to have an adapter. There's a special cable for this. Apparently, they didn't want to pay the royalty for the HMI, so they use that type of connector. And you guys doing commissioning work should have some kind of adapter in your toolkit so that if you need to see what this thing is doing and get to its desktop, that you can hook a video monitor up to it. Okay. So one of the things that you ought to do if you get a couple of minutes is get into that trainer and hook up a keyboard, mouse, and a video to it so you can go see what's there and have a look at configuring networks and installing software or whatnot on the IPC. We good?
Oh, yeah.
All right. So,
Dan, I have a quick question.
Yeah.
Earlier you were talking about how we have 24 volts to a bus, 24 volts to I/O slices, and then maybe a third power supply, and then you cut out there. What did you say there?
When there are things like motors where there's a high power or high noise kinds of devices. Sometimes they'll use yet another power supply to drive them. So a lot of times, yeah, a motor will have a 48-volt supply. Higher voltage keeps the wire gauge down, gives you more torque. Okay?
Thank you.
All right. So right up in here, you'll notice that there are two RJ45 ports. Okay, so at this point, I'm going to try to switch video sources. And this is going to be really exciting. Because I am going to try to switch video sources. Speakers video. All right. Did that switch video sources?
It did with your web camera, but not the presentation screen.
Okay. Let me see if I can get that over to that. How do I get it to show?
I think if you select the present now, I think a little pop-up window appears at the top when it asks you, and you can select which window you want to use. So you have a selection, but I don't see a selection for web camera or external camera, but that's because I don't have it connected.
So I don't see a mechanism for getting that video over to you. Can you maximize that screen so you can see it?
I think, yeah. If we pin it, then we can see it.
Yeah. All right, so pin it so you can see it.
That's the sort of ingenuity we need at commissioning.
All right, now I'm banking on the idea that you guys got that
We
done.
have some adapters that we can plug into those and the other IPCs as well. So we
I was going to go to Best Buy and get a couple.
some stuff.
We have keyboards in mind.
No, I'm talking for the screen, the DVI to HDMI, and we've got the display port HDMI ones as well.
I was just going to go to Best Buy before our trip and just get like
a keyboard,
mice, and then all of the cables that I could find in expensive price. Unless you know where they are.
Yeah, I know where they are.
Oh, okay, then perfect.
I know where one of them is.
Oh, thank God.
Yeah.
I misunderstood. I thought you were saying we're there somewhere.
No, we do, because we bought several of them, so we should be able to find them.
All right, sweet. Is he talking?
No, not. Okay, so you can see my cam. Okay, so just a little bit about EtherCAT, and it'll help set the context of what you're looking at in terms of this architecture. So back in the development of programmable logic controllers, the earliest ones that were done were built to replace rotating drums that were found in mechanical robotic systems. So you think about how a sewing machine works, with in essence, there's a motor that drives a cam, and the cam makes all kinds of things move up and down and rotate and push, and there's just a bunch of stuff that happens off of a cam. The nature of those machines was cyclical. Therefore, when we went to the electrical version of that, we made them cyclical. And for many years, as we developed PLCs, we developed custom hardware, and we stayed inside this notion of it being cyclical. So rather than state-oriented like a regular program would be, it's just a list of instructions, and when it's done with the list of instructions, the PLC will sit around and then repeat. Fine. There were a couple of things that happened with that architecture that really became, it became apparent that when you have a large factory floor and you've got these PLCs running, you really need some means of communicating data very, very quickly. And RS-232 and RS-485, and there's a whole bunch of technologies that emerged in serial communications that were pretty good, but you were lucky if you could get a 19.2 baud, sometimes 115K baud, but not terribly quick. So Hans Beckhoff realized that, well, maybe what we could do is use the Ethernet TCP/IP oriented hardware to solve this bandwidth problem. So, and you will see all kinds of Ethernet show up in the realm of PLCs. The great problem is that TCP/IP protocol is best effort. So while I might be able to get 100 megabits per second, you just don't know if packets are going to arrive. There's no deterministic timing. So what Beckhoff did is he tried to figure out a way to subvert the normal internet packet idea and try to make it a real-time, high-speed, deterministic field bus. And the way he accomplished that is when you get into the network interface chip, right, or the interface card, what used to happen is packets would come into a little thing of electronics. We would put the packets into a queue, and then we had a CPU that would have a look at what was in the queue, parse the packets out, and then decide what to do with them, to keep them, toss them out. The result of this old architecture was that packets would come in, but you depending on how many packets were being received by the queue, the CPU might get to it sooner or might get to it later. There was a lot of latency involved in it, and packets would age out. And if that happens, then you have to resend, and it's just a messy. It's a messy protocol if you want deterministic timing in communications. So Beckhoff nixed that. He said, what we'll do is we'll start it with an idea of a master. And the master will send a packet out. And what we'll do is the packet will be received by a slave. And on the inside of this, there'll be a shift register. So the packet will get clocked through a shift register. And then we'll have a CPU watching that shift register to see if whatever's in that packet is for me or for not for me. So there's this notion of a master, and there's a notion of a slave. Every slave picks up a packet and rebroadcasts a packet, and the packets are run through a shift register that is clocked. So if you know the clock rate of the shift register and you know the length of the shift register, then you can predict how much latency is involved with each slice. So it's still very deterministic. So that was his basic idea on the packet. So the protocol, the EtherCAT, uses the same drivers, the same wires, Yeah.
Hold on a second, Dan.
I have a question.
Yeah.
Can you, I'm not familiar with the shift register. Can you kind of like go over what a shift register is?
Ah, very good. So you have serial ones and zeros coming along, right? With me?
Yeah, I can hear you.
Okay. So we got this idea of a clock. This is cool stuff because you can build clocks that sync up and stuff like that. So anyway, you got this notion of a clock, and let's say on each clock, what we're going to do is I'm going to take whatever's in this cell and I'm going to move it over to the next one, right? And whatever's in that one, and I'm just going to walk it through a series of bits. So, initially, if my bits were walking in, the first time it might be the first clock, it would look like that. Second clock, it would go here. Third clock, see how they're kind of walking through?
Yeah.
So I'm shifting them through one bit at a time, and they're held in memory, right?
Yep.
So what happens then is, if this is 100 bits wide, then the time between this guy coming in here and then slowly working its way through all the registers and coming out the other side, it's just 100 times the clock rate. Furthermore, then the CPU can look at all 100 bits simultaneously and see if an address is for it or not.
Okay.
With me?
Yep.
Okay. So what that does in an architecture or in a system that you're looking at there, is because it uses all of exactly the same hardware. Now I'm going to try to switch back over to my other screen. In our training, this IPC is a bus master, and it has one of these shift register oriented network interface chips in it. Then each one of these slices, these individual components, are called a slave. And they have an equivalent network interface chip, an EtherCAT chip, in them. And what will happen is the master will generate a packet, pass it to the first slice. That first slice will run it through its shift register, then to the next one. It'll export it to the next slice. That slice will export it to the next slice. That slice will export it to the next one, and so on. When it gets to the end, the chips are designed so that they know when the daisy chain is ended, and it will actually turn the packet around and ship it back up to the master. So packet flow on the bus, on this E-bus, starts at the master, works its way through the slaves, turns around at the last slave, and comes back to the master. What that means is you could think of it as a train leaving the master, and each one of the slices has a car, and as the packet passes through these, the slices are looking for its particular address, and it loads and unloads data as the packet goes by, and then the packet makes its way back to the master. Right? So there's and the time that it takes to traverse this can be calculated by looking at the electrical propagation delay from one slice to another, which it's going to be, 100 megabits per second. It's going to be microseconds, nanoseconds, and then the time it spends in the shift register. So you can just do some quick math, and how long that packet will take to cycle through. Okay?
Yeah.
Okay. On this side, you'll notice there are two RJ45 jacks. These jacks are the electrical requirements for EtherCAT and TCP/IP are identical at the physical layer. So when you attach a factory network, which is a TCP/IP network, you're going to come into this top one. Okay. This bottom one could serve as a TCP/IP port, or it could be an EtherCAT port, depending on how it's wired up. We okay?
Yeah.
Okay. So what I'm looking at here is a power supply, the IPC, we call them. It's a Windows computer running a soft PLC. These are slices. This is a bus master. Packets are developed by the bus master, pass through the slices. That's one form of communication. We have a factory interface that we can tie to here, and we have the ability to expand the EtherCAT bus out this guy. Okay, we still on board?
Oh, yeah.
Okay. So the big idea is deterministic packet delivery, a soft PLC. Instead of custom hardware, we're using standard Windows hardware. There are 3 links right there that will take you through some really, really good explanations of exactly how EtherCAT works. Everyone, yeah.
I'm sorry. Is this shared with us on the Google Drive somewhere?
It will be.
This presentation. Okay, great. Thank you.
Absolutely. So everyone on this call must absolutely have dive into all 3 of these links, and it will give you a very clear picture of why EtherCAT is going to rule the world here as a bus protocol, I would say within the next 5 years. It's absolutely crystal clear to me that 5 years from now, when you go down and look at the light show down at Turtle Bay, it will be an EtherCAT light show. I mean, there's so much power in this stuff that is unrealized. It's just going to happen. So there's 3 links. I'll make sure that this share gets out to you guys so you have those links.
Thank you.
Okay, let's talk a little bit about the TwinCAT. So Beckhoff uses a soft PLC architecture, meaning that you can run shoot back over to my desk cam. And we'll just do a picture. It's the easiest way to do this. So the old school way of handling a PLC was to do a CPU, and the CPU would have the notion of a program, and we run the program in the link, and then it would have some form of an OS that was there for development purposes. And this architecture put us in a state where, you go out and you buy, Alan Bradley or somebody, you buy one of their controllers. The controllers would have a really light OS in it. And, you could do development and everything would be fine. You run the program. And a couple of weeks later, you want some other feature. And because the CPU and the OS are all proprietary, you'd find that you'd have to replace the CPU, replace the OS to get this new functionality. So on the hard PLCs, they have these families of products that, they're with different functions, different capabilities. And a lot of times when customers had to expand, the functionality of a PLC, they'd have to replace the PLC with some big thing, and they'd have to buy a new IDE and new code conversion. It was a mess. What Beckhoff did is they took standard PC hardware and they made a deal with Microsoft. So they run, in essence, they run a, not wrong words of core. I'll just say it's Beckhoff. Beckhoff time slices between the OS and the PLC code. So Beckhoff's in control of the hardware. They run Windows as a service, so they can guarantee the PLC software gets priority. So rather than run PLC software on Windows, Windows runs on their PLC software. It's flipped over. And that way they can stay with the deterministic timing. Okay, so going back over to my big screen, TwinCAT is just the integrated development environment that Beckhoff provides for doing PLC programming. If they could, they use standard industry components, and they tried to make it as generic as possible. So TwinCAT is Windows-based. It actually runs Microsoft's Visual Studio software, and then they bolt on the EtherCAT stuff onto Microsoft's Visual Studio. They implemented all 7 PLC languages at some level. They included support for reusable code and modules, and they tried to keep it non-proprietary, and it's free. So all to say that TwinCAT is not the only EtherCAT development environment, and Windows is not the only OS that TwinCAT can run on. Okay, do I need to pause there?
No, I think you're good.
Okay, so now let's talk about getting our IPC or PLC onto the network, okay? So you got a trainer, you walk into a factory network, and what are we going to do? Well, you're going to have a laptop sort of like the one that I've got here. And one of the things you can do, you guys can see my desktop. So can you see the icon down at the bottom? It's pretty small.
Oh, yeah.
Yeah. What we can do is we can actually run or TwinCAT, we can install TwinCAT IDE on a laptop that you can carry with you. It's just the development environment, okay? So, and it installs as a service, and there are a number of reasons why it does. And there's a number of training videos on installing TwinCAT that we have in the classroom files, and there's a bunch of stuff up on the web to do the same. But we use TwinCAT because it's so well aligned to the EtherCAT hardware. It's well supported in our relationship with Beckhoff. It's Windows based. You know, there's a lot of power to it. We love it for all those reasons. We hate it largely because it's Windows, and that has its own fun, shall we say. So I'm going to assume that I've got TwinCAT loaded onto a laptop. And my task is I want to get my laptop attached to this guy. Okay? So there's a couple of things. In that mode of connectivity, switch over to that other, my desktop again. TCP IP. So basically, the way this is going to work when we connect, we're going to have our laptop running TwinCAT 3. We're going to use the factory network or whatever that's going to tie out to our IPC. And then the IPC will use EtherCAT to talk to its slaves. So what that's going to look like, and we've, there's a lot of nightmare stories when we come into this. It's really tempting to take your laptop and your network adapter on your laptop and just plug an RJ, an EtherCAT cable from your laptop directly into this port on the IPC. And it can be done, but here's the trick, is this is a Windows CPU in essence, and its communication for TCP/IP have to have an IP address. And you can, if you're a network guy, you'll get this. But if you plug your laptop straight into this machine, your laptop is probably configured for DHCP. This guy's probably configured for DHCP. So the odds that they'll land on the same network is like nil. What's interesting is if you get through that, the actual mechanism that your laptop will use to communicate with this IPC after you make that initial contact uses a different protocol. So what happens is, sometimes by hook or by crook, you get it to work and it works fine for you. But when you switch laptops, then you can't talk to this guy anymore. It gets really funny, and it has to do with the way the two devices handle IP addressing and whether or not they can see each other. So my recommendation when you come into a factory is, if you can, plug this into the factory network and allow it to do a DHCP address. Have the target laptop that you're going to be working with plugged into the network so it gets an IP address. So you both got an IP address, right? So you've got the DHCP server. If that is not allowed, then I would recommend that with your video adapter, you might also carry a very small 4-port router that's configured to provide DHCP services. So what you would do is, even if the router doesn't get to the internet, if you plug your laptop into the router and the router gives your laptop an address, plug this thing into the router and the router will give this guy an address, and it will help the two machines find each other's IP addresses.
Hey, Dan.
Yeah.
Is there any way to set a static IP on the IPC?
Yes. Yes, there is. And you would have to set, so the path on that is there's a couple of paths. One path is to get in with a USB keyboard mouse monitor and go and configure this guy for a static IP. If you do that, do us all a favor and make sure you put a sticker on this thing that really says it loud and clear. Right? Because we're constantly losing those. Then you have to do the same thing on your laptop, and you got to make sure that the subnets are compatible. Okay?
Yep.
Even then, it can be a little hinky, and I can't tell you why, but we've had some issues with it. I'm kind of, when I'm in front of customers, I'm really about mitigating risks and not having issues that I don't want to bring issues into the room. So I've kind of settled in my mind. If it was my job, I would spend $50 and get a really lightweight router, and then their IT department will tell you how these things will be configured. And when you're doing commissioning, it's possible they will want to plug this into their factory network, which is fine. And that whole plugging kind of deal, there's a couple of ways to do it, but working through the keyboard mouse is an easy one. So once you've got this thing, both machines on a network, here's what's going to happen to you next. And we're watching my presentation screen. I click on the TwinCAT icon down here, and I'm going to fire up the TwinCAT development environment. Everybody seen this before?
Oh, yeah.
Oh, yeah. So what this IDE is, it's an integrated development environment, and meaning it's designed to allow us to write some software and test it out. It has the ability to emulate a PLC without actually being connected to real live hardware. So it does have that emulation mode. It also allows us to connect to the actual IPC, target IPC that we want to work with. So what I'm going to do is I'm going to attach to an IPC that I have here in my office. So what I'm going to do is I'm going to create a new project, and I'm going to create a TwinCAT project and give it a name. And I already have that one, so I'll give it a different name.
Have you been demoing for other teams, Dan?
I was up at 5:30 this morning trying to make sure that this would work. Okay.
Well, thank you. We appreciate it.
I just created a project, right? In the IDE, a project is a container, and you got to have a container in order to work with anything. So I just created an empty project container. Here in this box up here, I can choose to work with a local system, or I can choose to work with a remote IPC. So what I'm going to do is I'm going to go choose a target system. You have to be in local mode, and I'm going to search the Ethernet. So you'll recall my laptop is tied to like a factory network. The IPC is tied to a factory network. That network is running Ethernet. So what's going to happen is I'm going to actually do some broadcast searches and try to identify any of the TwinCAT masters that might happen to be in the network. So when I do a search, there's a bunch of options in here, but notice here the transport type is TCP/IP, right? Because I'm literally using the factory network backbone to search for my devices, or maybe it's local on your router, or if you got a point-to-point, it's still TCP/IP as the transport. Okay. And I don't know much about the device I'm looking for, so I will simply do a broadcast search. And on a good day, something will show up. Come on. It's still on.
The subnet's correct?
Static. Did I mention that even on a good day, the first connection is really interesting?
Do you know why this is so buggy?
Yes, I do. What's happening is it's running. So in the environment that I have, my laptop is wireless to a Google Nest. The Google Nest runs, so it puts me into a Google Nest that gives me DHCP, and then I'm using a wireless access point to bring it back into TCP/IP to my IPC. And it takes a while for the router to wake up the routes, and there's ARP tables and a bunch of stuff like that involved. And it takes some time for it to all wake up. And it's not uncommon to see what happened to me to happen. Or sometimes I have to back out, retry. It takes 2 or 3 times to get it woke up. But when it does, it did identify. This is the name of my IPC. There's the AMS ID that will be used to communicate with it once I get this set up. There's the IP address that was assigned to the device by my router. And it's kind of interesting because you can select to go by host name, and there's reason to do that. If this is not statically routed, this IP address could change, and that might cause problems for you to connect to it later on. You can go over to host name, and it will try to search by name. But in complicated network environments where you've got stuff like mesh networks, like I have, sometimes these broadcast things just are a little funky. So what happens is we say, fine, I'm going to go host name. I'm going to add a route. This is going to ask me for a password. Password is 1. That's one of those magic things that you need to keep in mind when you're confronted by a password challenge in Beckhoff world. Try the number 1.
Is that default for a lot of Beckhoff passwords?
Yeah.
Yeah.
Cool.
So what
Hey,
I
Dan.
did is I added the route. I'm going to close this.
Hey, Dan.
Yeah.
Is there does it expose anything other than the host name in that menu, or is that all we have to go off of for, if we're in a factory and they've got 10 of the same model PLCs on the network and you open that up and you're trying to pick one, you've got 10 with random host names, how are you going to know which one's correct?
When you are doing your inventory and whatnot, actually, I'm glad you asked that question. Let me switch back to this. This guy right here has a sticker on it, on one of these sides that has the name on it, right? And in the way I think, I would love to see those stickers put up to the front so that the names of these devices were clearly identified. Because you're right, you might have 20 of these on here, and the names of these switch numbers is really handy.
Yeah.
And the way that is, there is a sticker on them that has it, and it'd be great if it was brought up into a very visible place.
It would be cool if TwinCAT could expose the name of the project that's running on that IPC too, so you wouldn't have to have physical access to it to identify them.
On the one that Dan
and
has actually displayed on the LCD.
Oh, okay.
Yeah.
It's an interesting problem because some of them have a little LCD, some of them don't. Sometimes you might have a dozen or more of these little guys all over the place. Keeping track of who's where in the physical topology is a little bit rugged. So, I got that target system set up. When I select the target system, because the IPCs have different CPUs, as you can imagine, in any IDE, you've got to match the compiler to the type of CPU you have. So now I'm getting an error. Let's go back. There we go. Okay, so this one's an ARM, whatever, there it is. So this now, I have my CX2DE-B22, that's the name of it. I'm connected to it. And when I go down to I/O here, well, this section is all for coding. There's some other stuff that goes on in terms of licensing, and this is a big topic. But once I get to this point, now I can go out and have TwinCAT interrogate what's on the EtherCAT bus. So to do that, just to highlight a couple of things, you'll notice there's a couple of icons up here for restarting and whether or not you're in config mode. And we want to be in what's called a config mode. And once that's done, then once I'm in config mode, I can scan for devices. And what that will do is that will send a message to the IPC and tell it to interrogate its EtherCAT bus and discover all the devices that might be attached to it. So I'm asking it to do a scan, and it's going to run out there and do some stuff and scanning and starting, and you get a chance. It'll ask you sometimes about drives as it discovers them.
Does this only search the EtherCAT network or any of the networks it has connected to the IPC?
It will look on the far side of the IPC. So you came in the top port of the IPC. So it will go out the E-bus. Let me point this out again. Let's go back to here. I'm plugged into here with TCP/IP, right? And when I ask it to do a scan, it will scan for devices out this side, and it will scan for anything attached to this guy.
Okay.
So it's kind of looking around, and you saw when I did it, it registered a bunch of ports, and that's part of what was going on. So there were three places it could have looked, and as we expand them, you can see that it didn't find anything in this device for, it didn't find anything out the second RJ45 port, but it did find stuff in its local bus. This EK1200, it's worth diving into the documentation on these things and learning these slices, but this is a bridge in essence, and under that bridge is the list of slices. So if we go back to the picture, what you're looking at is we searched in here. It didn't find anything out this port, but this slice right here found a bunch of, this guy communicated to the EK slice, and then it found all these other devices out the other side. So when we go look, it found an EL2809, a 3314, 3001. Then if we expand it, the 2809 is a 16-channel output. Okay. And 3314 is a thermocouple. So let's see if I have a thermocouple. If I see what's going on, maybe 178. Yeah. So thermocouple is connected, and it thinks it's 17 Celsius in here. There's a decimal point, so it's 3-digit. You have to divide by 10. So it's measuring temperature. And then my third slice is something. Yeah.
So the thermocouple, do you actually have on the thermocouple slice? Do you actually have an input plugged into it, or is that just it's like home temperature?
I actually have I have something plugged in. I have a Type K thermocouple plugged in.
Okay, so that's how it's actually getting a reading. If you didn't have an input plugged into it, would it display anything?
Yeah, if you come into status, under range, over range, limits, errors, all these kinds of flags are available to you. So,
Dan, can I add a quick comment?
yes.
Just something that covers some of the content that a few of us talked about the other day. But the initial scan, which you showed us, is great, because then you can physically see that each slice is connected, or if there's issues with certain slices. And then you've jumped a layer into that now of actually looking at individual slices to validate that they are working or getting information, getting inputs or sending outputs.
So, if we were to switch back to my desktop again, each one of the slaves has an EtherCAT slave chip, and it actually has 4 ports on it. It's kind of interesting, and each port has there's a goes in and a goes out for each one of these. This is explained in more detail in those YouTubes and some of the other stuff. But attached to this EtherCAT network interface chip, there is a CPU in every one of these slices. And what the CPU does is it maintains a bunch of variables that refer to the state of the hardware underneath it. So literally, in the case of the temperature TC inputs, the EL3314, the ESC chip is picking up these packets and rebroadcasting. The CPU is checking the bits in that it sees in the shift register to see if it's for this unit or not. Meanwhile, the CPU is also monitoring the hardware, and it's putting information into a set of registers. Those registers will be passed into the packet and sent back up to the master. Since it's a CPU, we have an opportunity to do things like range checking, error checking. We could monitor power, temperature. What do you want to do? You could just kind of dream it up on a per slice basis, depending on what your slice does. You could dream up all kinds of things to put in the software of the CPU to keep track of what the hardware is doing, right? So almost all every slice is different in that respect in terms of what it will tell you and what it won't. But even if something is simple, I just want to measure temperature, under range, over range, limits, errors, and you go up to the Infosys system of Beckhoff, pull down the documentation on the slice, and you'll get 40, 50 pages of like what's on the slice, what's in the slice, what do these bits all mean, what do you do with them? So one of the tasks that's in front of us to be experts is to start diving into these slices and understanding them and programming them. And that literally is what customers are doing with those trainers. They're literally, it's a sandbox so that you can set up an environment like the one that I have set up here. You can throw some sensors on there really easily and then start looking at how these things work and how you can use them in the programming of your PLC. I should also mention Um, if this was a motor controller, it's also very possible, because I have a CPU and I have things like flash and all kinds of RAM, it's possible that you could have a very intelligent motor that would, like if it is an EtherCAT motor, you could put everything there is to know about the motor inside of this environment and then expose it through the EtherCAT interface. So, you get a NEMA 23 motor, and, you could literally put in it, here's how much power, here's the torque curve, here's, the temperature that it should run in, here's the voltages, here's the currents. And literally it's conceivable that in the not too distant future, we'll figure out how to have systems self-tune, because you have all of the data about all of the components in the components themselves. Which all to say is that when you come to deal with motors, you will find that it's a bit more complicated than it should be. And that's partly why, is because we're still halfway in between old school and new school. Couple other things. In this mode, I'm in free run mode. I can also toggle bits if you're interested. I can set an output bit high.
Make sure it's not connected to anything.
Yeah. You can force all kinds of stuff. And is that good or bad? As is pointed out, it could be a train wreck.
Dan, I would say this is important for the team to know, just for commissioning, making sure.
Yep. Okay, so we did a quick review of the EtherCAT Basics. We looked at TwinCAT Basics. We talked a little bit about PLC on the network, scanning drives, tuning drives, big topic. I want to talk a little bit about safety slices. You'll notice there are these orange devices out here. These are safety slices, and they're the architecture of the safety. Well, I should back up. The idea of a safety slice is, and when we're dealing with human safety, we're trying to keep people from. We're trying to build a machine that makes it idiot-proof so that people can't kill themselves. So in the early days, they did stuff like, if you had a big old giant saw or something and you wanted to make sure nobody walked into it, you might put a pad on the ground that had a weight sensor. And the idea was that if you stepped on this mat, it would shut off the saw, right? So that was pretty good, except that once in a while the mats would fail. And so they came up with the idea that a safety mat should be a mat that has two switches in it, not one switch. Maybe it has a normally open switch, and maybe it has a normally closed switch. And when you step on the pad, both switches must change state, right? Yeah. So if the pad was to break, if you had a bad pad, the question is, what are the odds that it would go bad in a way that they would both change state or both state? And it's conceivable, but not likely, right? So there's this notion of a thing called a safety device, and an EMO, emergency off button, is one of them, that implement this idea of dual hardware. So the next thing that happens is, how do you know if it's plugged in? And one answer is I could run a very quick pulse down the wire and see if it acts like a short, right? I could actually energize, put a little microsecond pulse on the cabling and detect if something that I think is a closed switch is really a closed switch. And so that was implemented in these slices. They have a piggyback circuit that can ping the wires to see if a switch is there. So you can see a broken wire. Another thing they'll do is they say, well, what if the computer running all of that freezes? And the answer is, well, I'll have two computers running in parallel, and I'll put in some watchdog timers so that if it freezes, I know, or if the two vote differently, I'll know. And so these slices are designed really to try to give a machine that level of confidence in the logic that it's running.
So, hey, Dan, something interesting I think that we ran into at Tesla was that little ping of electricity that you're talking about to make sure that the circuit is still good. We had a situation where a switch wasn't compatible with that ping, and so it wouldn't work. So it was confusing the switch, and so the switch wouldn't work. And so we had to actually turn that off to make the switch work again. It was a switch for opening a door to turn the machine off.
Really interesting, isn't it? Because, you know, in the old days, this stuff goes back, the ideas go back to the old sewing machine cams. And they thought switches were switches that click on and click off. But then you put a FET switch on something, and you're right, it doesn't work the same. Really true. Yeah. Yeah. And this is, you know, yeah, finding those kinds of things. This is why we check every wire, is because those kinds of things will exist in the design. Just that way. So
something to add to that, Dan, and Matt, is this is also with Tesla. You talked about a pulse, and you have several different pulse settings that you can set through the safety so that it knows it's not getting back a false 24 volts or something that didn't come from it, which is also smart.
So when we go to working with the safety, there are a couple of things that are unique about it. I described some of the hardware in these slices that is different. One of the other thing that's different is the programming is fundamentally different. And in the Beckhoff environment, it's actually its own program. You know, if we go back to the Beckhoff IDE, and you'll notice that we can have a PLC project, you can have a motion project, and you also can have a safety project. And it's treated as its own code. So it's a separate project within the project. And so when we're dealing with safety, it's one of those areas that is as specialized as motors. You have to have hardware connected to it to test it. You have to have software running, and I mean it has to be software that is functional. You can't really test safety without things being fairly mature. And then the other piece of it is they're very concerned about people cheating with safety. And so there are additional safeguards, including dip switches on the sides of these modules, so that these modules are addressed. So there's a set of dip switches on these things. And what happens then is when you're writing your software is tied to those dip switches. So if somebody tries to swap something out, it kind of screws the system up and it goes into a safety mode. It generally means it doesn't do much. So part of what happens in commissioning of these safety systems is you'll have to get with whoever designed the safety system and whoever is dealing with the architecture of these safety systems, and you'll have to get from them what they want these addresses to be. Generally speaking, they need to be set to a unique address on the network, and so it's one of those things. Because the wires come out of the front of this, you'll want to get that done early, so you know what these should be. And again, you can't see the switches once you get them installed, so sometimes it's nice to have a label or something that tells you what's there.
Dan, that'll actually prevent the system from working completely, so it's one of the first things that needs to be done.
Say more, Roger.
That'll actually prevent the system from working completely, because you won't be able to scan everything in if they've got the same dip switch settings on them, especially if they're similar slices. So if you've got a number of 1904s together and they're all set to dip switch setting 1, it won't scan them all in. It'll throw an error in the system. So they have to be set before anything can be done.
And on these DIN rail systems, the wires come out the front, right?
Yeah.
And to get these slices out, you can see really closely, there's a little orange thing right there. It's really hard to see. But what you do is you get in there and you pull that thing out, and it releases the DIN rail latch, and you can slide that slice out of the stack. But you're flexing all of the wires going into these connectors. And I really resonate with what Roger's saying. You don't want to be pulling those modules out after you've checked the wires. You really don't. So, getting those switches done early, that's great advice.
And a needle nose pliers is one of your best friends for taking those out as well. It's much easier than getting your fingers around the orange tab.
So, Roger, where did you get the safety code for dealing with this stuff when you were doing commissioning at Sela and Tesla?
They have to be unique.
Didn't I ask you a question, Roger?
Sorry, what was that, Dan?
Where did you get the code so that you could run those safety systems when you were working with customers?
Usually directly from our contact. When we were at Sela, they had it all uploaded to GitHub, and we were able to connect to it that way. At Tesla, I'm trying to remember. I think
that at Tesla, actually, Greg connected his laptop directly to the machine and downloaded it.
He did, yeah, because we talked to what was the name of the company that had the winder machines? We talked directly to them about connecting into it, and that's the only way we could get it. So.
They have to be unique, although
they have to be unique. So you got 2, 4, 6, 8, 10, 12, 4, or 2, 4, 8, 16, 32, 64, 128, 2, 56. Sure about that? And then the top row goes further. So if on your inputs, you're always going to have more inputs than outputs on a safety system.
Right.
So the outputs generally only have one bank of dip switches. The inputs have 2. And it'll be the same with
each of the safety slices have to be unique.
They have to be unique. And it's the same with the EJ modules, is one of the ones that plug into the PCBs.
Okay. Thanks.
Sorry, go ahead, Dan.
So, I don't know what else to tell you in this session about safety, except for, this is another mountain we all need to climb. In my opinion, all of us should be able to write a very, very quick safety program. But it is a skill position. It's not as easy to do as one might think. It's a whole mindset. So I'll let that lie with that.
Dan, I do have another question.
Yeah.
For the safety slices, the dip switches, does that matter? Like when let's say if I were to design it, as long as all of them are different, can I just set them to any number?
Yes.
Or, okay.
So, my mind immediately goes to what are they? 12-bit, Roger?
Yeah, I think so.
So you got 12 bits to deal with, so you might use 4 bits for factory, 4 bits for building, you can imagine kind of coming up with some kind of a coding scheme or something. But as long as they're unique, that's the key thing.
Okay.
So a lot of our customers will generally specify how they want them to be done as well, because it helps with their programming on their side. So like with applied materials panels, if there's safety slices in it, they'll generally specify that we want the first one to be set to 1, then 2, 3, 4, 5, 6, like that. Some people will want them to be specific numbers that will match with the actual number of the slice in the code. So if it's terminal 36, they might want to start at a terminal 36, but it's always worth consulting with the customer to find out. And it's also worth noting it as well, so that you can just say to the customer, hey, we've set these and these are the values, because if in the future one of the slices dies, it's easier for the customer to know, oh, I need to replace it and put in a new one with dip switch settings that are set to this, and then I can scan it in and run the system immediately, instead of having to look for a new slice that's affecting how the system works.
Okay, so it's 11:41. One other topic that I want to show you. If you Google, what is it, Beckhoff? Is that sufficient? No.
You miss an H in there.
Are you looking for infosys.beckhoff.com?
So there are a couple of websites that will really help. Beckhoff, just in terms of the way they think about things, Beckhoff is inclined to dump more information on you than you could ever imagine wanting. And they have 2 websites. One is this Beckhoff.com, and the other one, what is it, Infosys, Roger?
Yeah, it's linked from the front page on the Beckhoff page.
It's weird because
And one of them is more, sales oriented, and the other one is more technology oriented or tech oriented. Okay. So what you can do in this thing is inside of this, if you expand things out, you can find information on every one of their products. Like we were dealing with the price was a 3314 or something. It was a thermocouple input. Where is it? Thermocouples. There it is. I think we were looking at a 3314. And this gives you a breakdown of all the stuff, related products, and you can dive into all the bits and pieces. I don't know how you could survive commissioning without being very familiar with using those 2 websites. So if you haven't done it already, I've got no recommendation other than to say, take the time, stay up late, a couple evenings or something, and crawl through this and have a look at just the amazing amount of stuff that's here. Get familiar with it. Almost anything and everything you could imagine wanting to know is here somewhere. The problem is finding it. The Google search engine does a decent job of penetrating this website. So a lot of times if you Google something specific, about an EL or an EJ slice, it will direct you into this website. So rather than using this search, you can use a Google search.
One of the other things that's useful for Dan is if you just leave that screen up there on the right-hand side, it shows you the schematic of the slice. For some reason or other, Beckhoff doesn't always pair their channels in the same direction. Sometimes they're vertical and sometimes they're horizontal across a slice. So it can lead to wiring issues. So if people find that they can't get response either into or out of a slice, that's one of the things to look at first.
Yeah, and even understanding what these LEDs mean, all that kind of stuff, this is a great place to know about.
Yeah, we use that a lot down in Tesla because a lot of the machines had actually slices that were wired in wrong.
Wow.
Okay, so we've got 15 minutes to talk about anything you want to talk about.
Can we look at drives real quick?
Yes, we can. How do you look at drives? Motion. There are a lot of different kinds of drives, ranging from small to some very pretty good size drives. Roger, what's the best way to do this? If you had to explain something on drives, how would you do it?
Well, the ones the drive slices that you have called up there are for your 24, 48 volt motors. Beckhoff actually has some huge drives as well that are like 5-6 pounds in weight that get mounted separately into some of the systems. The winders in Tesla all used these type of drives. If anybody saw the pictures or saw them, they were all mounted horizontally along the top of the machine. I think there was 6 or 7 Beckhoff ones and a couple of Panasonics. A lot of customers are tending to go with Panasonic because they are actually better with EtherCAT than Beckhoff, which is slightly ironic, and you can also get them. One of the notable things about the larger servo drives, the AX series that you've got on the screen there, is that the basic drive doesn't come with a lot in it, and if you're looking for specific safety things, there's cards that plug into the top of them that you don't have to wire in separately. It basically adds an internal circuit into the drive that will allow it to do things like safe torque off and multiple other safety features that needed to be done inside them. So when you get into motion, you can I'm just trying to think through what we did in Tesla. So on the winders, we were able to disable the drives from the system so that we could incrementally move them to ensure that they were moving correctly.
So, you know, I should point out there's a fundamental architecture difference between Beckhoff's approach to motors and others. Most of us are comfortable with the idea of an indexer driver, where you've got, you know, the electronic circuits that actually push the motor, the driver, and then you've got some brains, and we send it, you know, G code or something, and the brains turn it into stuff, and the encoder information is tied to the indexer. In the Beckhoff world, the intelligence of the motor drive is brought back up into the IPC. So those drives are really pretty simple. They're going to rotate the motor. They're going to provide some safety and some stop information, you know, some things like that. But the indexer is a software module in the IPC. So from a commissioning perspective, once again, You know, it's not like you can just send a couple of commands to an indexer and get it to move. I think you'll find that what you end up having to do is when you scan, you'll see the motor drive appear as a terminal. And there are some features that you can use to jog and enable and disable, but to actually get motors to do much, you almost have to write some software. And that is a big distinction between Beckhoff and regular indexer drivers. So for what that's worth.
So also on some of the installs with commissioning, just for testing, we basically overrode the STO through supplying 24 volt, and then just use that jog feature. And there's some nice like jog to and fro, but strictly for testing. You don't want to release it at all to customers like that. The other thing I'll say is the BIN, the Beckhoff Integrated Network, has some really good training for motion. It's probably about 2 hours, maybe 3, but take some time, run through that, especially with the trainer in front of you if you could, and that will stitch up really well for the motion side.
I was just asking if anyone's, talked about the types of moves yet. And one thing that I want to caution is that, there's specifically what I want to talk about is the difference between like a velocity move and then a torque move. And you want to make sure that you understand which moveset you're in before you command the motor to do anything, because it actually could be easy to get a runaway motor and cause damage to something.
It might be really good to make sure, maybe what we need to do is set up kind of a thing to make sure that our team members have had a chance to work with this tech before they get onto a customer site. Maybe some kind of internal certification thing. Because that, safety is its own beast. Motors are their own beast. DIO is a thing, IPCs, there's a lot here.
Yeah, Jay was actually pinging Ken at Beckhoff about putting some kind of testing in place for all the training they're doing, so that we could go through the trainings on the online trainings and then actually have some kind of testing to certified staff. So hopefully that's coming soon.
Here on my cam, I've got a slice out. If you haven't seen a slice, this is what they look like. On the top side, push wires, there's a specialty screwdriver. Roger can show you, or one of the guys can show you, there's a screwdriver that goes in there that releases a little spring clip, LEDs on the top side. There's the release mechanism for the DIN rail, and when I pull on it, you'll see it's flattening that out so it releases it off the rail, and then it literally just slides up off the other units. The power and the E-bus comes down these connections that are on each side. Literally, the EtherCAT packets are brought in on these springs and then rebroadcast out on the other side, and the rest of these are powers and grounds. Other topics?
Hey, Dan, did you want to talk about passive slices?
Say more, Roger.
So you can have passive slices in a system and it won't scan them in. It won't actually see them, but they will still be there. So passive slices are generally ones that begin EL9 something. They don't communicate across the E-bus, but they're there to provide power or something like that into the system. So the advantage of it is if we come across a system that needs, something we did in Tesla was they had all their safety slices together, and there was a concern that they were going to generate a lot of heat. So we added in passive slices in between the safety slices, and it means that the code doesn't need to be changed at all in the system, and it will continue to work perfectly well. Every system that gets scanned in will automatically add in an EL9011 at the end of it, which is the plastic slice that covers the E-bus terminals. So if you're scanning in a system and you see that happening and you don't know what it is and you think I didn't add that in, whether you have it on the end of it or not, TwinCAT will scan it in. But yeah, passive slices, I think they normally show up with an orange color in TwinCAT to let you know that they're not actually pulling from the E-bus current.
So again, I'm up on the Beckhoff website, and if you look under the EL9000 series, there's just a bootload of very interesting different slices that you can get that does, as Roger mentioned, everything from electrical isolation to inject more power into the buses to, I think there's some that provide capacitance.
Yeah.
Yeah, there's a buffer capacitor for 48 volt. Okay, well, we're coming up on the 12 mark. Ned, you have anything else? Do we want to schedule a second session, or how are we doing?
I did have one more thing I'd probably want to like more clarification on, and it was like an explanation on the slide that's right next to the PLC and how the different how it powers the slices and other components in the panel. So like the E-bus, like the different way you're able to distribute power with that slice.
I'm going to try to pull one up. So on my screen, this is a CX 2040.
Yeah.
Right. And Ethernet, USB stuff, status LEDs. Right on this side, right there is a connector. And on, did I lose my presentation?
No, we can see you.
I wanted to get that picture. I wanted to get the picture of that. Let me go find things. The picture of the slice that we have there. There it is. So on the unit, the trainers, right next to the IPC is a power injection slice. That's this little guy right there. Okay. And it actually has some DC-DC converters and some isolators in there. And its job is to inject power into the bus. And part of the power comes over to power the CPU and whatnot. Part of the power is run through a DC-DC converter to power the E-bus, which is actually a 3.3 volt bus. And then the other connector is brought out to all the stuff that connects to external hardware.
Hold on, Dan.
Yeah.
You say that there's actually ADC in that slice in the CX2100. It converts AC to DC, or is the power supply doing that?
It's a DC-DC.
Oh, thank you.
Yeah, not an AC. No, it's a DC-DC converter. And the classic mistake is you get one wired up and forget about the other. Or, you know, there's a number of things that happen. That slice is, what is that, a 12 something?
Is it a 2100?
Yeah.
Yeah.
It's a 2100?
Yeah.
So if we go to terminals and 21 EL.
It's a CX 2100.
Oh, I'm thinking of the
Power Boost slice.
EK 1200. So you can see it right there. It called it an EK. Let me look at this. EK. EJ. Here I go wandering.
Are you looking for the couplers, Dan?
Yeah.
EK 1100 is the series. EK 1101, EK 1110.
You can actually get that slice just on the phone.
Yeah, it's not connected to the controller. It's not a slice rather, it's more of like a module. That's
Yeah.
exactly what it is. Yeah, you can get that slice because just what might happen is that you might have, I think it's like the EK 1200 or something where you actually connect it, like on your CX 2017, you connect to another EtherCAT like module with EtherCAT, and then you still need to have that slice right there to do the DC to DC conversion for the slices, right? So you'll have your EtherCAT communication, like the EK 12 or whatever it is, and then you'll have this slice, and then you'll have your slices after that. And then, but then the difference is instead of connecting this in line with the IPC, you're connecting it with your EtherCAT protocol with a Cat 5 or Cat 6 shielded cable. Makes sense? I think we have something here in office that I can bring in and show you. So yeah, in this case, it's a single module that's connected to the IPC. In other cases, they're separate things.
Okay.
Okay, anything else?
Thanks so much for doing this, Dan. I really appreciate it.
Well, you know, the other tidbit that I would give you is, you know, when you guys are down doing commissioning and it starts to go sideways, just remember you've got a really good team behind you. And, you know, if it gets dicey, make a phone call. It's okay.
Phone home.
It's I do it. and it's just comforting to know sometimes that you can put a phone call in and get some help or get another set of eyes. I use a lot of FaceTime when I'm in the field, so I can hold my phone up and show people what I'm looking at. And between all of us, I think we can solve any of these problems. Okay, with that said, I think we're about done.
Thanks so much.
That was so helpful. Thank you.
Thank you, Dan.
Thanks, Dan.
Thank you, Dan.
Okay,
I'll be calling you all weekend when I have all these questions.
that's great, man. Look forward to hearing about it.
All right, bye.
All right, see you guys.
Thank you. Bye.